Hi, my name's Tim Roughgarden. I'm a professor here at Stanford University, and I'd like to welcome you to this first course on the design and analysis of algorithms. Now, I imagine many of you are already clear on your reasons for taking this course, but let me begin by justifying this course's existence and giving you some reasons why you should be highly motivated to learn about algorithms. So, what is an algorithm anyways? Basically, it's a set of well-defined rules, a recipe in effect, for solving some computational problem. Maybe you have a bunch of numbers and you want to rearrange them so that they're in sorted order. Maybe you have a roadmap and an origin and a destination, and you want to compute a shortest path from that origin to that destination. Maybe you face a number of different tasks that need to be completed by certain deadlines, and you want to know in what order you should accomplish the tasks so that you complete them all by their respective deadlines. So why study algorithms? Well, first of all, understanding the basics of algorithms and the related field of data structures is essential for doing serious work in pretty much any branch of computer science. This is the reason why, here at Stanford, this course is required for every single degree that the department offers: the bachelor's degree, the master's degree, and also the PhD. To give you a few examples, routing and communication networks piggybacks on classical shortest path algorithms. The effectiveness of public key cryptography relies on that of number theoretic algorithms. Computer graphics needs the computational primitives supplied by geometric algorithms. Database indices rely on balanced search tree data structures. Computational biology uses dynamic programming algorithms to measure genome similarity, and the list goes on. Second, algorithms play a key role in modern technological innovation. To give just one obvious example, search engines use a tapestry of algorithms to efficiently compute the relevance of various web pages to a given search query. The most famous such algorithm is the PageRank algorithm, currently in use by Google. Indeed, in a December 2010 report to the United States White House, the President's Council of Advisors on Science and Technology argued that in many areas, performance gains due to improvements in algorithms have vastly exceeded even the dramatic performance gains due to increased processor speeds. Third, although this is outside of the scope of this course, algorithms are increasingly being used to provide a novel lens on processes outside of computer science and technology. For example, the study of quantum computation has provided a new computational viewpoint on quantum mechanics. Price fluctuations in economic markets can be fruitfully viewed as an algorithmic process, and even evolution can be usefully thought of as a surprisingly effective search algorithm. The last two reasons for studying algorithms might sound flippant, but both have more than a grain of truth to them. I don't know about you, but back when I was a student, my favorite classes were always the challenging ones that, after I struggled through them, left me feeling a few IQ points smarter than when I started. I hope this course provides a similar experience for many of you. Finally, I hope that by the end of the course I'll have converted some of you to agree with me that the design and analysis of algorithms is simply fun. It's an endeavor that requires a rare blend of precision and creativity. It can certainly be frustrating at times, but it's also highly addictive. So let's now descend from these lofty generalities and get much more concrete. And let's remember that we've all been learning about and using algorithms since we were little kids. Sometime when you were a kid, maybe say third grade or so, you learned an algorithm for multiplying two numbers. Maybe your third grade teacher didn't call it that. Maybe that's not how you thought about it. But you learned a well-defined set of rules for transforming an input, namely two numbers, into an output, namely their product. So that is an algorithm for solving a computational problem. Let's pause and be precise about it. Many of the lectures in this course will follow a pattern. We'll define a computational problem, we'll say what the input is, and then we'll say what the desired output is. Then we will proceed to giving a solution, to giving an algorithm that transforms the input into the output. When the integer multiplication problem, the input is just two n-digit numbers. So the length, n, of the two input integers x and y could be anything, but for motivation you might want to think of n as large, in the thousands or even more. Perhaps we're implementing some kind of cryptographic application which has to manipulate very large numbers. We also need to explain what is the desired output. In this simple problem, it's simply the product x times y. So a quick digression. So back in third grade, around the same time I was learning this integer multiplication algorithm, I got a C in penmanship, and I don't think my handwriting has improved much since. Many people tell me, by the end of the course, they think of it fondly as a sort of acquired taste. But if you're feeling impatient, please note there are typed versions of these slides, which I encourage you to use as you go through the lectures, if you don't want to take the time deciphering the handwriting. Returning to the integer multiplication problem, having now specified the problem precisely, the input, the desired output, we'll move on to discussing an algorithm that solves it, namely the same algorithm you learned in third grade. The way we will assess the performance of this algorithm is through the number of basic operations that it performs. And for the moment, let's think of a basic operation as simply adding two single-digit numbers together or multiplying two single-digit numbers. We're going to then move on to counting the number of these basic operations performed by the third grade algorithm as a function of the number n of digits in the input. Here's the integer multiplication algorithm that you learned back in third grade, illustrated on a concrete example. Let's take, say, the numbers 1, 2, 3, 4, and 5, 6, 7, 8. As we go through this algorithm quickly, let me remind you that our focus should be on the number of basic operations this algorithm performs as a function of the length of the input numbers, which in this particular example is 4 digits long. So as you'll recall, we just compute one partial product for each digit of the second number. So we start by just multiplying 4 times the upper number, 5, 6, 7, 8. So, 4 times 8 is 32, 2, carry the 3, 4 times 7 is 28. With the 3, that's 31, write down the 1, carry the 3, and so on. When we do the next partial product, we do a shift. Effectively, we add a 0 at the end, and then we just do exactly the same thing. And so on for the final two partial products. And finally, we just add everything up. What you probably realized back in third grade is that this algorithm is what we would call correct. That is, no matter what integers x and y you start with, if you carry out this procedure, this algorithm, and all of your intermediate computations are done properly, then the algorithm will eventually terminate with the product x times y of the two input numbers. You're never going to get a wrong answer. You're always going to get the actual product. What you probably didn't think about was the amount of time needed to carry this algorithm out to its conclusion, to termination. That is, the number of basic operations, additions or multiplications of single-digit numbers needed before finishing. So let's now quickly give an informal analysis of the number of operations required as a function of the input length n. Let's begin with the first partial product, the top row. How did we compute this number 22,712? Well, we multiplied 4 times each of the numbers 5, 6, 7, and 8. So that was 4 basic operations, 1 for each digit of the top number, plus we had to do these carries, so those were some extra additions. But in any case, this is at most twice times the number of digits in the first number, at most 2n basic operations to form this first partial product. And if you think about it, there's nothing special about the first partial product. The same argument says that we need at most 2n operations to form each of the partial products, of which there are again n, one for each digit of the second number. Well, if we need at most 2n operations to compute each partial product, and we have n partial products, that's a total of at most 2n squared operations to form all of these blue numbers, all of the partial products. Now, we're not done at that point. We still have to add all of those up to get the final answer, in this case 7,006,652, and that final addition requires a comparable number of operations, roughly another, say, 2n squared at most operations. So the upshot, the high-level point that I want you to focus on is that as we think about the input numbers getting bigger and bigger, that is, as a function of n, the number of digits in the input numbers, the number of operations that the grade school multiplication algorithm performs grows like some constant, roughly 4, say, times n squared. That is, it's quadratic in the input length n. For example, if you double the size of the input, if you double the number of digits in each of the two integers that you're given, then the number of operations you will have to perform using this algorithm has to go up by a factor of 4. Similarly, if you quadruple the input length, the number of operations is going to go up by a factor of 16, and so on. Now, depending on what type of third grader you were, you might well have accepted this procedure as the unique, or at least the optimal way of multiplying two numbers together to form their product. Now, if you want to be a serious algorithm designer, that kind of obedient timidity is a quality you're going to have to grow out of. An early and extremely important textbook on the design and analysis of algorithms was by Aho, Hockcroft, and Ullman. It's about 40 years old now. And there's the following quote, which I absolutely adore. So after iterating through a number of the algorithm design paradigms covered in the textbook, they say the following: perhaps the most important principle of all for the good algorithm designer is to refuse to be content. And I think this is a spot-on comment. I might summarize it a little bit more succinctly as an algorithm designer, you should adopt as your mantra the question, can we do better? This question is particularly apropos when you're faced with a naive or straightforward solution to a computational problem, like, for example, the third grade algorithm for integer multiplication. A question you perhaps did not ask yourself in third grade was, can we do better than the straightforward multiplication algorithm? And now is the time for an answer. If you want to multiply two integers, is there a better method than the one we learned back in third grade? To give you the final answer to this question, you'll have to wait until I provide you with a toolbox for analyzing divide and conquer algorithms a few lectures hence. What I want to do in this lecture is convince you that the algorithm design space is surprisingly rich. There are certainly other interesting methods of multiplying two integers beyond what we learned in third grade. And the highlight of this lecture will be something called Karatsuba multiplication. Let me introduce you to Karatsuba multiplication through a concrete example. I'm going to take the same pair of integers we studied last lecture, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to execute a sequence of steps resulting in their product. But that sequence of steps is going to look very different than the one we undertook during the grade school algorithm. Yet, we'll arrive at exactly the same answer. The sequence of steps will strike you as very mysterious. It'll seem like I'm pulling a rabbit out of a hat. In the rest of this video, we'll develop more systematically what exactly this Karatsuba multiplication method is and why it works. But what I want you to appreciate already on this slide is that the algorithm design space is far richer than you might expect. There's a dazzling array of options for how to actually solve problems like integer multiplication. Let me begin by introducing some notation for the first and second halves of the input numbers x and y. So the first half of x, that is 56, we're going to regard as a number in its own right called A. Similarly, B will be 78, C will be 12, and D will be 34. I'm going to do a sequence of operations involving only these double-digit numbers A, B, C, and D. And then after a few such operations, I will collect all of the terms together in a magical way, resulting in the product of X and Y. First, let me compute the product of A times C and also the product of B times D. I'm going to skip the elementary calculations and just tell you the answer. So you can verify that A times C is 672, whereas B times D is 2652. Next, I'm going to do something even still more inscrutable. I'm going to take the sum of A and B, I'm going to take the sum of C and D, and then I'm going to compute the product of those two sums. That boils down to computing the product of 134 and 46, namely 6164. Now, I'm going to subtract our first two products from the results of this computation. That is, I'm going to take 6164, subtract 2652, and subtract 672. You should check that if you subtract the results of the first two steps from the result of the third step, you get 2840. Now, I claim that I can take the results of steps 1, 2, and 4 and combine them in a super simple way to produce the product of X and Y. Here's how I do it. I start with the first product, AC, and I pad it with 4 zeros. I take the result of the second step and I don't pad it with any zeros at all. And I take the result of the fourth step and I pad it with 2 zeros. If we add up these three quantities from right to left, we get 2, 5, 6, 6, 0, 0, 7. If you go back to the previous lecture, you'll note that this is exactly the same output as the grade school algorithm. That is, this is in fact the product of 1, 2, 3, 4, and 5, 6, 7, 8. So let me reiterate that you should not have any intuition for the computations I just did. You should not understand what just went down on this slide. Rather, I hope you feel some mixture of bafflement and intrigue. But more to the point, I hope you appreciate that the third grade algorithm is not the only game in town. There's fundamentally different algorithms for multiplying integers than what you learned as a kid. Once you realize that, once you realize how rich the space of algorithms is, you have to wonder, can we do better than that third grade algorithm? In fact, does this algorithm already do better than the third grade algorithm? Before I explain full-blown Karatsuba multiplication, let me begin by explaining a simpler, more straightforward recursive approach to integer multiplication. Now, I am assuming you have a bit of programming background, in particular that you know what recursive algorithms are. That is, algorithms which invoke themselves as a subroutine with a smaller input. So how might you approach the integer multiplication problem recursively? Well, the input are two digits, two numbers, each has n digits. So to call the algorithm recursively, we need to form inputs that have smaller size, less digits. Well, we already were doing that in the computations on the previous slide. For example, the number 5, 6, 7, 8, we treated the first half of the digits 56 as a number in its own right, and similarly 78. In general, given a number x with n digits, it can be expressed, decomposed, in terms of two n over 2 digit numbers, namely as a, the first half of the digits shifted appropriately, that is multiplied by 10 raised to the power n over 2, plus the second half of the digits b. In our example, we had a equal to 56, 78 was b, n was 4, so 10 to the n over 2 was 100, and then c and d were 12 and 34. What I want to do next is illuminate the relevant recursive calls. To do that, let's look at the product x times y, express it in terms of these smaller numbers a, b, c, and d, and do an elementary computation. Multiplying the expanded versions of x and y, we get an expression with three terms, one shifted by 10 raised to the power n, and the coefficient there is a times c. We have a term that's shifted by 10 to the n over 2, and that has a coefficient of AD and also plus BC. And bringing up the rear, we have the term B times D. We're going to be referring to this expression a number of times, so let me both circle it and just give it a shorthand. We're going to call this expression star. One detail I'm glossing over for simplicity is that I've assumed that n is an even integer. Now, if n is an odd integer, you can apply this exact same recursive approach to integer multiplication in the straightforward way. So if n was 9, then you would decompose one of these input numbers into, say, the first 5 digits and the latter 4 digits, and you would proceed in exactly the same way. Now, the point of expression star is if we look at it, despite being the product of just elementary algebra, it suggests a recursive approach to multiplying two numbers. If we care about the product of x and y, why not instead compute this expression star, which involves only the products of smaller numbers, a, b, c, and d. You'll notice, staring at the expression star, there are 4 relevant products, each involving a pair of these smaller numbers, namely AC, AD, BC, and BD. So why not compute each of those 4 products recursively? After all, the inputs will be smaller. And then once our 4 recursive calls come back to us with the answer, we can formulate the rest of expression star in the obvious way. We just pad A times C with n zeros at the end. We add up AD and BC using the grade school algorithm and pad the result with n over 2 zeros. And then we just sum up these 3 terms, again using the grade school addition algorithm. So the one detail missing that I've glossed over, required to turn this idea into a bona fide recursive algorithm, would be to specify a base case. As I hope you all know, recursive algorithms need a base case. If the input is sufficiently small, then you just immediately compute the answer rather than recursing further. Of course, recursive algorithms need a base case so they don't keep calling themselves till the rest of time. So for integer multiplication, what's the base case? Well, if you're given 2 numbers that have just 1 digit each, then you just multiply them in one basic operation and return the result. So what I hope is clear at the moment is that there is indeed a recursive approach to solving the integer multiplication algorithm, resulting in an algorithm which looks quite different than the one you learned in 3rd grade, but which nevertheless you could code up quite easily in your favorite programming language. Now, what you shouldn't have any intuition about is whether or not this is a good idea or a completely crackpot idea. Is this algorithm faster or slower than the grade school algorithm? You'll just have to wait to find out the answer to that question. Let's now refine this recursive algorithm, resulting in the full-blown Karatsuba multiplication algorithm. To explain the optimization behind Karatsuba multiplication, let's recall the expression we were calling star on the previous slide. So this just expressed the product of x and y in terms of the smaller numbers a, b, c, and d. In the straightforward recursive algorithm, we made 4 recursive calls to compute the 4 products which seemed necessary to compute the expression star. But if you think about it, there's really only 3 quantities in star that we care about, the 3 relevant coefficients. We care about the numbers AD and BC not per se, but only in as much as we care about their sum, AD plus BC. So this motivates the question, if there's only 3 quantities that we care about, can we get away with only 3 rather than 4 recursive calls? It turns out that we can, and here's how we do it. The first coefficient AC and the third coefficient BD we compute exactly as before, recursively. Next, rather than recursively computing AD or BC, we're going to recursively compute the product of A plus B and C plus D. If we expand this out, this is the same thing as computing AC plus AD plus BC plus BD. Now here is the key observation in Karatsuba multiplication, and it's really a trick that goes back to the early 19th century mathematician Gauss. Let's look at the quantity we computed in step 3 and subtract from it the 2 quantities that we already computed in steps 1 and 2. Subtracting out the result of step 1 cancels the AC term. Subtracting out the result of step 2 cancels out the BD term, leaving us with exactly what we wanted all along, the middle coefficient AD plus BC. And now, in the same way that on the previous slide we had a straightforward recursive algorithm making 4 recursive calls and then combining them in the obvious way, here we have a straightforward recursive algorithm that makes only 3 recursive calls, and on top of the recursive calls does just grade school addition and subtraction. So you do this particular difference between the 3 recursively computed products, and then you do the shifts, the padding by zeros, and the final sum as before. So that's pretty cool, and this kind of showcases the ingenuity which bears fruit even in the simplest imaginable computational problems. Now, you should still be asking the question, is this crazy algorithm, is it really faster than the grade school algorithm that we learned in 3rd grade? Totally not obvious. We will answer that question a few lectures hence, and we'll answer it as a special case of an entire toolbox I'll provide you with to analyze the running time of so-called divide and conquer algorithms like Karatsuba multiplication. So stay tuned. In this video, I'll talk about various aspects of the course, the topics that we'll cover, the kinds of skills you can expect to acquire, the kind of background that I expect, the supporting materials, and the available tools for self-assessment. Let's start with the specific topics that this course is going to cover. The course material corresponds to the first half of a 10-week Stanford course that's taken by all computer science undergraduates, as well as many of our graduate students. There will be 5 high-level topics, and at times these will overlap. The 5 topics are, first of all, the vocabulary for reasoning about algorithm performance, the design and conquer algorithm design paradigm, randomization in algorithm design, primitives for reasoning about graphs, and the use and implementation of basic data structures. The goal is to provide an introduction to and basic literacy in each of these topics. Much more can be said about each of them than we'll have time for here. The first topic is the shortest and probably also the driest, but it's a prerequisite for thinking seriously about the design and analysis of algorithms. The key concept here is big O notation, which conceptually is a modeling choice about the granularity with which we measure a performance metric, like the running time of an algorithm. It turns out that the sweet spot for clear, high-level thinking about algorithm design is to ignore constant factors and lower-order terms and to concentrate on how well algorithm performance scales with large input sizes. Big O notation is the way to mathematicize this sweet spot. Now, there's no one silver bullet in algorithm design, no single problem-solving method that's guaranteed to unlock all of the computational problems that you're likely to face. That said, there are a few general algorithm design techniques, high-level approaches to algorithm design that find successful application across a range of different domains. These relatively widely applicable techniques are the backbone of a general algorithms course like this one. In this course, we'll only have time to deeply explore one such algorithm design paradigm, namely that of divide and conquer algorithms. In the sequel course, as we'll discuss, there's 2 other major algorithm design paradigms that get covered. But for now, a divide and conquer algorithm, the idea is to first break the problem into smaller subproblems, which then get solved recursively, and then to somehow quickly combine the solutions to the subproblems into one for the original problem that you actually care about. So for example, in the last video, we saw 2 algorithms of this sort, 2 divide and conquer algorithms for multiplying 2 large integers. In later videos, we'll see a number of different applications. We'll see how to design fast divide and conquer algorithms for problems ranging from sorting to matrix multiplication to nearest neighbor type problems in computational geometry. In addition, we'll cover some powerful methods for reasoning about the running time of recursive algorithms like these. As for the third topic, a randomized algorithm is one that, in some sense, flips coins while it executes. That is, a randomized algorithm will actually have different executions if you run it over and over again on a fixed input. It turns out, and this is definitely not intuitive, that allowing randomization internal to an algorithm often leads to simple, elegant, and practical solutions to various computational problems. The canonical example is randomized quicksort, and that algorithm and analysis we will cover in detail in a few lectures. Randomized primality testing is another killer application that we'll touch on, and we'll also discuss a randomized approach to graph partitioning, and finally we'll discuss how randomization is used to reason about hash functions and hash maps. One of the themes of this course, and one of the concrete skills that I hope you take away from the course, is literacy with a number of computational primitives for operating on data that are so fast that they're in some sense essentially free. That is, the amount of time it takes to invoke one of these computational primitives is barely more than the amount of time you're already spending just examining or reading the input. When you have a primitive which is so fast that the running time is barely more than what it takes to read the input, you should be ready to apply it, for example, in a pre-processing step, whenever it seems like it might be helpful. It should just be there on the shelf waiting to be applied at will. Sorting is one canonical example of a very fast, almost for-free primitive of this form. But there are ones that operate on more complex data as well. So recall that a graph is a data structure that has, on the one hand, vertices, and on the other hand, edges, which connect pairs of vertices. Graphs model, among many other things, different types of networks. So even though graphs are much more complicated than mere arrays, there are still a number of blazingly fast primitives for reasoning about their structure. In this class, we'll focus on primitives for computing connectivity information and also shortest paths. We'll also touch on how such primitives have been used to investigate the structure of information in social networks. Finally, data structures are often a crucial ingredient in the design of fast algorithms. A data structure is responsible for organizing data in a way that supports fast queries. Different data structures support different types of queries. I'll assume that you're familiar with the structures that you typically encounter in a basic programming class, including arrays and vectors, lists, stacks, and queues. Hopefully, you've seen at some point both trees and heaps, or you're willing to read a bit about them outside of the course, but we'll also include a brief review of each of those data structures as we go along. There's two extremely useful data structures that we'll discuss in detail. The first is balanced binary search trees. These data structures dynamically maintain an ordering on a set of elements while supporting a large number of queries that run in time logarithmic in the size of the set. The second data structure we'll talk a fair bit about is hash tables or hash maps, which keep track of a dynamic set while supporting extremely fast insert and lookup queries. We'll talk about some canonical uses of such data structures, as well as what's going on under the hood in a typical implementation of such a data structure. There's a number of important concepts in the design and analysis of algorithms that we won't have time to cover in this 5-week course. Some of these will be covered in the sequel course, Design and Analysis of Algorithms 2, which corresponds to the second half of Stanford's 10-week course on this topic. The first part of this sequel course focuses on two more algorithm design paradigms. First of all, the design and analysis of greedy algorithms with applications to minimum spanning trees, scheduling, and information theoretic coding. And secondly, the design and analysis of dynamic programming algorithms, with example applications being in genome sequence alignment and shortest path protocols in communication networks. The second part of the sequel course concerns NP-complete problems and what to do about them. Now, NP-complete problems are problems that, assuming a famous mathematical conjecture you might have heard of, which is called the P not equal to NP conjecture, are problems that cannot be solved under this conjecture by any computationally efficient algorithm. We'll discuss the theory of NP-completeness, and with a focus on what it means for you as an algorithm designer. We'll also talk about several ways to approach NP-complete problems, including fast algorithms that correctly solve special cases, fast heuristics with provable performance guarantees, and exponential time algorithms that are qualitatively faster than brute force search. Of course, there are plenty of important topics that can't be fit into either of these two 5-week courses. Depending on the demand, there might well be further courses on more advanced topics. Following this course is going to involve a fair amount of time and effort on your part. So, it's only reasonable to ask, what can you hope to get out of it? What skills will you learn? Well, primarily, even though this isn't a programming class per se, it should make you a better programmer. You'll get lots of practice describing and reasoning about algorithms. You'll learn algorithm design paradigms, so really high-level problem-solving strategies that are relevant for many different problems across different domains, and tools for predicting the performance of such algorithms. You'll learn several extremely fast subroutines for processing data, and several useful data structures for organizing data that can be deployed directly in your own programs. Second, while this is not a math class per se, we'll wind up doing a fair amount of mathematical analysis, and this in turn will sharpen your mathematical and analytical skills. You might ask, why is mathematics relevant for a class in the design and analysis of algorithms, seemingly more of a programming class? Well, let me be clear. I am totally uninterested in merely telling you facts or regurgitating code that you can already find on the web or in any number of good programming books. My goal here in this class, and the way I think I can best supplement the resources that you probably already have access to, is to explain why things are the way they are, why we analyze the algorithms in the way that we do, why various superfast algorithms are in fact superfast, and so on. And it turns out that good algorithmic ideas usually require non-trivial mathematical analysis to understand properly. You'll acquire fundamental insights into the specific algorithms and data structures that we discuss in the course, and hopefully many of these insights will prove useful more generally in your other work. Third, and perhaps most relevant for those of you who work in some other discipline, this course should help you learn how to think algorithmically. Indeed, after studying algorithms, it's hard not to see them pretty much everywhere. whether you're riding an elevator, watching a flock of birds, buying and selling stocks out of your portfolio, or even watching an infant learn. As I said in the previous video, algorithmic thinking is becoming increasingly useful and prevalent in fields outside of computer science and technology, like in biology, statistics, and economics. Fourth, if you're interested in feeling like a card-carrying computer scientist in some sense, then you'll definitely want basic literacy in all of the topics that we'll be covering. Indeed, one of the things that makes studying algorithms so fun is it really feels like you're studying a lot of the greatest hits from the last 50 years of computer science. So after this class, no longer will you feel excluded at that computer science cocktail party when someone cracks a joke about Dijkstra's algorithm. Now you'll know exactly what they mean. Finally, there's no question that studying this material is helpful for technical interview questions. To be clear, my sole goal here is to teach you algorithms and not to prepare you for interviews per se. But over the years, countless students of mine have regaled me with stories about how mastering the concepts in this class enabled them to ace every technical question they were ever asked. I told you, this is fundamental stuff. So what do I expect from you? Well, honestly, the answer is nothing. After all, isn't the whole point of a free online class like this one that anyone can take it and devote as much effort to it as they like? So that said, as a teacher, it's still useful to have one or more canonical students in mind, and I thought I'd go ahead and be transparent with you about how I'm thinking about these lectures, who I have in mind that I'm teaching to. Though again, please don't feel discouraged if you don't conform to this canonical student template. I'm happy to have the opportunity to teach you about algorithms, no matter who you are. So first, I have in mind someone who knows at least some programming. For example, consider the previous lecture. We talked about a recursive approach to multiplying two numbers, and I mentioned how a certain mathematical expression, back then we labeled it star and circled it in green, how that expression naturally translated into a recursive algorithm. In particular, I was certainly assuming that you had some familiarity with recursive programs. If you feel comfortable with my statement in that lecture, if you feel like you could code up a recursive integer multiplication algorithm based on the high-level outline that I gave you, then you should be in good shape for this course. You should be good to go. If you weren't comfortable with that statement, well, you might not be comfortable with the relatively high and conceptual level at which we discuss programs in this course. But I encourage you to watch the next several videos anyways to see if you get enough out of them to make it worth your while. Now, while I'm aiming these lectures at people who know some programming, I'm not making any assumptions whatsoever about exactly which programming languages you know. Any standard imperative language, something like C, Java, or Python, is totally fine for this course. Now, to make these lectures accessible to as many programmers as possible, and to be honest, also to promote thinking about programming at a relatively abstract and conceptual level, I won't be describing algorithms in any particular programming language. Rather, when I discuss algorithms, I'll use only high-level pseudocode or often simply English. My inductive hypothesis is that you are capable of translating such a high-level description into a working program in your favorite programming language. In fact, I strongly encourage everyone watching these lectures to do such a translation of all of the algorithms that we discuss. This will ensure your comprehension and appreciation of them. Indeed, many professional computer scientists and programmers don't feel that they really understand an algorithm until they've coded it up. Many of the course's assignments will have a problem in which we ask you to do precisely this. Put another way, if you're looking for a sort of coding cookbook, code that you can copy and paste directly into your own programs without necessarily understanding how it works, then this is definitely not the course for you. There are several books out there that cater to programmers looking for such coding cookbooks. Second, for these lectures I have in mind someone who has at least a modest amount of mathematical experience, though perhaps with a fair bit of accumulated rust. Concretely, I expect you to be able to recognize a logical argument, that is, a proof. In addition, two methods of proof that I hope you've seen before are proofs by induction and proofs by contradiction. I also need you to be familiar with basic mathematical notation, like the standard quantifier and summation symbols. A few of the lectures on randomized algorithms and hashing will go down much easier for you if you've seen discrete probability at some point in your life. But beyond these basics, the lectures will be self-contained. You don't even need to know any calculus, save for a single simple integral that magically pops up in the analysis of the randomized quicksort algorithm. I imagine that many of you have studied math in the past, but you could use a refresher. You're a bit rusty. And there's plenty of free resources out there on the web, and I encourage you to explore and find some that you like. But one that I want to particularly recommend is a great set of free lecture notes. It's called Mathematics for Computer Science. It's authored by Eric Lehman and Tom Layton, and it's quite easy to find on the web if you just do a web search. And those notes cover all of the prerequisites that we'll need in addition to tons of other stuff. In the spirit of keeping this course as widely accessible as possible, we're keeping the required supporting materials to an absolute minimum. Lectures are meant to be self-contained and will always provide you with the lecture notes in PowerPoint and PDF format. Once in a while, we'll also provide some additional lecture notes. No textbook is required for this class, but that said, most of the material that we'll study is well covered in a number of excellent algorithms books that are out there. So I'll single out 4 such books here. The first 3 I mentioned because they've all had a significant influence on the way that I both think about and teach algorithms. So it's natural to acknowledge that debt here. One very cool thing about the second book, the one by Dasgupta, Papadimitriou, and Vazirani, is that the authors have made a version of it available online for free. And again, if you search on the authors' names and the textbook title, you should have no trouble coming up with it with a web search. Similarly, that's the reason I've listed the 4th book. Those authors have likewise made essentially complete version of that book available online, and it's a good match with the material that we're going to cover here. If you're looking for more details about something covered in this class or simply a different explanation than the one that I give you, all of these books are going to be good resources for you. There are also a number of excellent algorithms textbooks that I haven't put on this list. I encourage you to explore and find your own favorite. In our assignments, we'll sometimes ask you to code up an algorithm and use it to solve a concrete problem that is too large to solve by hand. Now, we don't care what programming language or development environment you use to do this, as we're only going to be asking you for the final answer. Thus, we're not requiring anything specific, just that you are able to write and execute programs. If you need help or advice about how to get set up with a suitable coding environment, we suggest that you ask other students for help via the course discussion forum. Finally, let's talk a bit more about assessment. Now, this course doesn't have official grades per se, but we will be assigning weekly homeworks. Now, we're going to assign homeworks for 3 different reasons. The first is just for self-assessment. It's to give you the opportunity to test your understanding of the material so that you can figure out which topics you've mastered and which ones that you haven't. The second reason we do it is to impose some structure on the course, including deadlines, to provide you with some additional motivation to work through all of the topics. Deadlines also have a very important side effect that it synchronizes a lot of the students in the class, and this of course makes the course discussion forum a far more effective tool for students to seek and provide help in understanding the course material. The final reason that we give homeworks is to satisfy those of you who, on top of learning the course material, are looking to challenge yourself intellectually. Now, this class has tens of thousands of students, so it's obviously essential that the assignments can be graded automatically. Now, we're currently only in the 1.0 generation of free online courses such as this one, so the available tools for auto-graded assessment are currently rather primitive. So we'll do the best we can, but I have to be honest with you. It's difficult or maybe even impossible to test deep understanding of the design and analysis of algorithms using the current set of tools. Thus, while the lecture content in this online course is in no way watered down from the original Stanford version, the required assignments and exams we'll give you are not as demanding as those that are given in the on-campus version of the course. To make up for this fact, we'll occasionally propose optional algorithm design problems, either in a video or via a supplementary assignment. We don't have the ability to grade these, but we hope that you'll find them interesting and challenging, and that you'll discuss possible solutions with other students via the course discussion forum. So I hope this discussion answered most of the questions that you have about the course. Let's move on to the real reason that we're all here, to learn more about algorithms. Okay, so in this video we'll get our first sense of what it's actually like to analyze an algorithm, and we'll do that by first of all reviewing a famous sorting algorithm, namely the merge sort algorithm, and then giving a really fairly mathematically precise upper bound on exactly how many operations the merge sort algorithm requires to correctly sort an input array. So I feel like I should begin with a bit of an apology. Here we are in 2012, a very futuristic sounding date, and yet I'm beginning with a really quite ancient algorithm. So for example, merge sort was certainly known to John von Neumann all the way back in 1945. So what justification do I have for beginning a modern class in algorithms with such an old example? Well, there's a bunch of reasons. One I haven't even put down on the slide, which is like a number of the algorithms we'll see, merge sort is an oldie but a goodie. So it's over 60 or maybe even 70 years old, but it's still used all the time in practice. Okay, so this really is one of the methods of choice for sorting. It's the standard sorting algorithm in a number of programming libraries. So that's the first reason. But there's a number of others as well that I want to be explicit about. So first of all, throughout these online courses, we'll see a number of general algorithm design paradigms, ways of solving problems that cut across different application domains. And the first one we're going to focus on is called the divide and conquer algorithm design paradigm. So in divide and conquer, the idea is you take a problem, you break it down into smaller subproblems, which you then solve recursively, and then you somehow combine the results of the smaller subproblems to get a solution to the original problem that you actually cared about. And merge sort is still, to this day, perhaps the most transparent application of the divide and conquer paradigm. It'll just be very clear what the paradigm is, what analysis challenges it presents, and what kind of benefits you might derive. As far as the benefits, so for example, you're probably all familiar with the sorting problem. Probably you know some number of sorting algorithms, perhaps including merge sort itself. And merge sort is better than a lot of the sort of simpler and I would say more obvious sorting algorithms. So for example, 3 other sorting algorithms that you might well know about, but that I'm not going to discuss here. If you don't know them, I encourage you to look them up in a textbook or look them up on the web. But so 3 sorting algorithms which are perhaps simpler. First of all is selection sort. So this is where you do a number of passes through your array, repeatedly identifying the minimum of the elements that you haven't looked at yet. So you do basically a linear number of passes, each time doing a minimum computation. There's insertion sort, which is still useful in certain cases in practice, as we'll discuss. But again, it's generally not as good as merge sort, where you just maintain the invariant that the prefix of the array is a sorted version of those elements. So after 10 loops of insertion sort, you'll have the invariant that whatever the first 10 elements of the array are, they're going to be in sorted order. And then when insertion sort completes, you have an entire sorted array. Finally, some of you may know about bubble sort. This is where you identify adjacent pairs of elements which are out of order, and you do repeated swaps until in the end the array is completely sorted. Again, I just say this to jog your memory. These are simpler sorts than merge sort, but all of them are worse in the sense that they all have performance in general, which scales with n squared when the input array has n elements. So they all have, in some sense, quadratic running time. But if we use this non-trivial divide and conquer approach, or non-obvious approach, we'll get, as we'll see, a much better running time than this quadratic dependence on the input. Okay, so we'll get a win for sorting in divide and conquer, and merge sort is the algorithm that realizes that benefit. So a second reason that I want to start out by talking about the merge sort algorithm is to help you calibrate your preparation. I think the discussion we're about to have will give you a good signal for whether your background's at about the right level of the audience that I'm thinking about for this course. So in particular, when I describe the merge sort algorithm, you'll notice that I'm not going to describe it in a level of detail that you could just translate it line by line into a working program in some programming language. My assumption, again, is that you're a solid enough programmer that you can take the high-level idea of the algorithm, how it works, and you're perfectly capable of turning that into a working program in whatever language you see fit. So hopefully, I don't, it may not be easy, the analysis of merge sort or the discussion of merge sort, but I hope that you find it at least relatively straightforward, because as the course moves on, we're going to be discussing algorithms and analyses which are a bit more complicated than the one we're about to do with merge sort. So in other words, I think this will be a good warm-up for what's to come. Now, another reason I want to discuss merge sort is that our analysis of it will naturally segue into discussion of how we analyze algorithms in this course and in general. So we're going to expose a couple of assumptions in our analysis. We'll focus on worst case behavior. We'll look for guarantees on performance, on running time that hold for every possible input of a given size. And it will also expose our focus on so-called asymptotic analysis, meaning we'll be much more concerned with the rate of growth of an algorithm's performance than on things like lower order terms or on small changes in constant factors. Finally, we'll do the analysis of merge sort using what's called a recursion tree method. So this is a way of counting up the total number of operations that are executed by an algorithm. And as we'll see a little bit later, this recursion tree method generalizes greatly, and it will allow us to analyze lots of different recursive algorithms, lots of different divide and conquer algorithms, including the integer multiplication algorithm that we discussed in an earlier segment. So those are the reasons to start out with merge sort. So what is the computational problem that merge sort is meant to solve? Well, presumably you all know about the sorting problem, but let me tell you a little bit about it anyways, just so that we're all on the same page. So we're given as input an array of n numbers in arbitrary order. And the goal, of course, is to produce an output array where the numbers are in sorted order, let's say from smallest to largest. Okay, so for example, we could consider the following input array, and then the goal would be to produce the following output array. Now, one quick comment. You'll notice that here in the input array, it had 8 elements and all of them were distinct. It was the different integers between 1 and 8. Now, the sorting problem really isn't any harder if you have duplicates. In fact, it can even be easier. But to keep the discussion as simple as possible, let's just among friends, go ahead and assume that they're distinct for the purpose of this lecture. And I'll leave it as an exercise, which I encourage you to do, which is to think about how the merge sort algorithm implementation and analysis would be different, if at all, if there were ties. Okay? But we'll go ahead and make the distinctness assumption for simplicity from here on out. Okay, so before I write down any pseudocode for merge sort, let me just show you how the algorithm works using a picture. And I think it'll be pretty clear what the code would be, even just given a single example. So let's go ahead and consider the same unsorted input array that we had on the previous slide. So the merge sort algorithm is a recursive algorithm, and again that means that it's a program which calls itself, and it calls itself on smaller subproblems of the same form. Okay, so the merge sort is, its purpose in life is to sort the given input array. So it's going to spawn off calls of itself on smaller arrays. And this is going to be a canonical divide and conquer application where we simply take the input array, we split it in half, we solve the left half recursively, we solve the right half recursively, and then we combine the results. So let's look at that in the picture. So the first recursive call gets the first four elements, the left half of the array, namely 5, 4, 1, and 8, and of course the other recursive call is going to get the rest of the elements, 7, 2, 6, and 3. You can imagine these as being copied into new arrays before they're given to the recursive calls. Now, by the magic of recursion, or by induction if you like, the recursive calls will do their task. They will correctly sort each of these arrays of 4 elements, and we'll get back sorted versions of them. So from our first recursive call, we receive the output 1, 4, 5, 8, and from the second recursive call, we receive the sorted output 2, 3, 6, 7. So now all that remains to complete merge sort is to take the two results of our recursive calls, these two sorted elements of length 4, and combine them to produce the final output, namely the sorted array of all 8 of the input numbers. And this is the step which is called the merge. And hopefully you already are thinking about how you might actually implement this merge in a computationally efficient way, but I do owe you some more details, and I will tell you exactly how the merge is done. In effect, you just walk pointers down each of the two sorted subarrays, copying over, populating the output array in sorted order. But I will give you some more details in just a slide or two. So that's merge sort in a picture. Split it in half, solve recursively, and then have some slick merging procedure to combine the two results into a sorted output. Okay, so let's move on and actually discuss the pseudocode for the merge sort algorithm. First, let me just tell you the pseudocode, leaving aside exactly how the merging subroutine is implemented. And this high level should be very simple and clear at this point. So there's going to be 2 recursive calls, and then there's going to be a merging step. Now, I owe you a few comments because I'm being a little sloppy. Again, as I promised, this isn't something you would directly translate into code, although it's pretty close. But so what are a couple of the ways that I'm being sloppy? Well, first of all, there's, in any recursive algorithm, you got to have some base cases. You got to have this idea that when the input's sufficiently small, you don't do any recursion, you just return some trivial answer. So in the sorting problem, the base case would be if you're handed an array that has either 0 or 1 elements, well, it's already sorted, there's nothing to do, so you just return it without any recursion. Okay, so to be clear, I haven't written down the base cases, although of course you would if you were actually implementing merge sort. So let me make a note of that. A couple other things I'm ignoring. I'm ignoring what to do if the array has odd length. So if it has, say, 9 elements, obviously you have to somehow break that into 5 and 4 or 4 and 5. So you would do that just in either way, and that would be fine. And then secondly, I'm ignoring the details of what it really means to sort of recursively sort. So for example, I'm not discussing exactly how you would pass these subarrays onto the recursive calls. That's something that really would depend somewhat on the programming language. So that's exactly what I want to avoid. I really want to talk about the concepts which transcend any particular programming language implementation. So that's why I'm going to describe algorithms at this level. Okay. All right, so the hard part, relatively speaking then, is how do you implement the merge step? The recursive calls have done their work. We have these 2 sorted subarrays of half the numbers, the left half and the right half. How do we combine them into one? And in English, I already told you on the last slide, the idea is you just populate the output array in sorted order by traversing pointers or just traversing through the 2 sorted subarrays in parallel. So let's look at that in some more detail. Okay, so here is the pseudocode for the merge step. So let me begin by introducing some names for the characters in what we're about to discuss. So let's use C to denote the output array. So this is what we're supposed to spit out with the numbers in sorted order. And then I'm going to use A and B to denote the results of the two recursive calls. Okay, so the first recursive call has given us array A, which contains the left half of the input array in sorted order. Similarly, B contains the right half of the input array, again, in sorted order. So as I said, we're going to need to traverse the two sorted subarrays A and B in parallel. So I'm going to introduce a counter, I, to traverse through A, J to traverse through B. I and J will both be initialized to 1 to be at the beginning of their respective arrays. And now we're going to do a single pass through the output array, populating it in increasing order, always taking the smallest from the union of the two sorted subarrays. And if there's one idea in this merge step, it's just the realization that the minimum element that you haven't yet looked at in A and B has to be at the front of one of the two lists. Right? So, for example, at the very beginning of the algorithm, where is the minimum element overall? Well, whichever of the two arrays it lands in, A or B, it has to be the smallest one there. Okay, so the smallest element overall is either the smallest element in A or it's the smallest element in B. So you just check both places. The smaller one's the smallest, you copy it over, and you repeat, and that's it. So the purpose of K is just to traverse the output array from left to right. That's the order we're going to populate it. We're currently looking at position I in the first array and position J in the second array. So that's how far we've gotten, how deeply we've probed into both of those two arrays. We look at which one has the current smallest, and we copy the smallest one over. Okay, so if the entry in the ith position of A is smaller, we copy that one over. Of course, we have to increment I. We probe one deeper into the list A, and symmetrically for the case where the current position in B has the smaller element. Now again, I'm being a little bit sloppy so that we can focus on the forest and not sort of and not get bogged down with the trees. I'm ignoring some end cases. So if you really wanted to implement this, you'd have to add a little bit to keep track of when you fall off either A or B. Okay, so you'd have additional checks for when I or J reaches the end of the array, at which point you copy over all the remaining elements into C. All right, so I'm going to give you a cleaned up version of that pseudocode so that you don't have to tolerate my questionable handwriting any longer than is absolutely necessary. This again is just the same thing that we wrote on the last slide, okay, the pseudocode for the merge step. Now, so that's the merge sort algorithm. Now let's get to the meaty part of this lecture, which is, okay, so merge sort produces a sorted array. What makes it, if anything, better than much simpler non-divide and conquer algorithms like, say, insertion sort? In other words, what is the running time of the merge sort algorithm? Now, I'm not going to give you a completely precise definition of what I mean by running time, and there's good reason for that, as we'll discuss shortly. But intuitively, you should think of the running time of an algorithm. You should imagine that you're just running the algorithm in a debugger. Okay? And every time you press enter, you advance one line in the program through the debugger, and then basically the running time is just the number of operations executed, the number of lines of code executed. So the question is how many times you have to hit enter on your debugger before the program finally terminates. So we're interested in how many such lines of code get executed for a merge sort when the input array has n numbers. Okay, so that's a fairly complicated question. So let's start with a more modest goal. Rather than thinking about the number of operations executed by merge sort, which is this crazy recursive algorithm which is calling itself over and over and over again, let's just think about how many operations are going to get executed when we do a single merge of two sorted subarrays. That seems like it should be an easier place to start. So let me remind you the pseudocode of the merge subroutine. Here it is. So let's just go and count up how many operations are going to get used. So there's the initialization step. So let's say that I'm going to charge us one operation for each of these two initializations. So let's call this two operations to set I equal 1 and J equal 1. Then we have this for loop. So clearly the for loop executes a total number of n times. So in each of these n iterations of this for loop, how many instructions get executed? Well, we have one here. We have a comparison. So we compare AI to BJ. And either way the comparison comes up, we then do two more operations. We do an assignment here or here, and then we do an increment of the relevant variable, either here or here. So that's going to be 3 operations per iteration. And then maybe I'll also say that in order to increment k, we're going to call it a 4th iteration. Okay, so for each of these n iterations of the for loop, we're going to do 4 operations. All right. So putting it all together, what do we have as the running time for merge? So let's say the upshot. So the upshot is that the running time of the merge subroutine, given an array of m numbers, is at most 4m plus 2. So a couple of comments. First of all, I've changed a letter on you, so don't get confused. In the previous slide, we were thinking about an input size of n. Here I've just I've changed the name of the variable to m. That's going to be convenient once we think about merge sort, which is recursing on smaller subproblems. But it's exactly the same thing, mn whatever. So an array of m entries, it does at most 4m plus 2 lines of code. The second thing is there's some ambiguity in exactly how we counted lines of code on the previous slide. So maybe you might argue that really each loop iteration should count as 2 operations, not just 1, because you don't just have to increment k, but you also have to compare it to the upper bound of n. Maybe. Would have been 5m plus 2 instead of 4m plus 2. So it turns out these small differences in how you count up the number of lines of code executed are not going to matter, and we'll see why shortly. So amongst friends, let's just agree, let's call it 4m plus 2 operations for merge to execute on an array of exactly m entries. So let me abuse our friendship now a little bit further with an inequality which is true but extremely sloppy. But I promise it'll make our lives just easier in some future calculations. So rather than 4m plus 2, this 2 is sort of getting on my nerves, let's just call this at most 6m, because m is at least 1. Okay? You have to admit, it's true, 6m always is at least 4m plus 2. It's very sloppy. These numbers are not anything close to each other for m large, but let's just go ahead and be sloppy in the interests of future simplicity. Okay? Now, I don't expect anyone to be impressed with this rather crude upper bound in the number of lines of code that the merge subroutine needs to finish, to execute. The key question, you recall, was how many lines of code does merge sort require to correctly sort the input array, not just this subroutine. And in fact, analyzing merge sort seems a lot more intimidating because it keeps spawning off these recursive versions of itself. So the number of recursive calls, the number of things we have to analyze is blowing up exponentially as we think about various levels of the recursion. Now, if there's one thing that we have going for us, it's that every time we make a recursive call, it's on quite a bit smaller input than what we started with. It's on an array of only half the size of the input array. So there's some kind of tension between, on the one hand, explosion of subproblems, a proliferation of subproblems, and the fact that successive subproblems only have to solve smaller and smaller subproblems. And resolving these two forces is what's going to drive our analysis of merge sort. So the good news is I'll be able to show you a complete analysis of exactly how many lines of code merge sort takes, and I'll be able to give you, in fact, a very precise upper bound. Okay, so here's going to be the claim that we're going to prove in the remainder of this lecture. So the claim is that merge sort never needs more than 6 times n times the logarithm of n, log base 2 if you're keeping track, plus an extra 6n operations to correctly sort an input array of n numbers. Okay, so let's discuss for a second, is this good? Is this a win, knowing that this is an upper bound on the number of lines of code that merge sort takes? Well, yes it is, and it shows the benefits of the divide and conquer paradigm. Recall, in the simpler sorting methods that we briefly discussed, like insertion sort, selection sort, and bubble sort, I claimed that their performance was governed by a quadratic function of the input size. That is, they need a constant times n squared number of operations to sort an input array of length n. Merge sort, by contrast, needs at most a constant times n times log n. Not n squared, but n times log n lines of code to correctly sort an input array. So to get a feel for what kind of win this is, let me just remind you, for those of you that are rusty or for whatever reason have lived in fear of the logarithm, just exactly what the logarithm is. Okay? So the way to think about the logarithm is as follows. So you have the x-axis, or you have n, which is going from 1 up to infinity. And for comparison, let's think about just the identity function. Okay? So the function which is just f of n equals n. Okay? And let's contrast this with the logarithm. So what is the logarithm? Well, for our purposes, we can just think of the logarithm as follows. Okay, so the log of n, log base 2 of n, is you type the number n into your calculator. Okay? Then you hit divide by 2. And then you keep repeating dividing by 2. And you count how many times you divide by 2 until you get a number that drops below 1. Okay? So if you plug in 32, you got to divide 5 times by 2 to get down to 1. Log base 2 of 32 is 5. If you put in 1,024, you have to divide by 2 10 times until you get down to 1. So log base 2 of 10,024 is 10, and so on. Okay? So the point is, you can already see this. If log of 1,000, roughly, is something like 10, then the logarithm is much, much smaller than the input. Okay, so graphically, what the logarithm is going to look like is it's going to look like a curve which becomes very flat very quickly as n grows large. Okay, so f of n being log base 2 of n, and I encourage you to do this perhaps a little more precisely on a computer or a graphing calculator at home, but log is going much, much, much slower than the identity function. And as a result, sorting algorithm which runs in time proportional to n times log n is much, much faster, especially as n grows large, than a sorting algorithm with a running time that's a constant times n squared. In this video, we'll be giving a running time analysis of the merge sort algorithm. In particular, we'll be substantiating the claim that the recursive divide and conquer merge sort algorithm is better, has better performance than simpler sorting algorithms that you might know, like insertion sort, selection sort, and bubble sort. So in particular, the goal of this lecture will be to mathematically argue the following claim from an earlier video, that in order to sort an array of n numbers, the merge sort algorithm needs no more than a constant times n log n operations. That's the maximum number of lines of code it will ever execute. Specifically 6 times n log n plus 6n operations. So how are we going to prove this claim? We're going to use what is called a recursion tree method. The idea of the recursion tree method is to write out all of the work done by the recursive merge sort algorithm in a tree structure, with the children of a given node corresponding to the recursive calls made by that node. The point of this tree structure is it will facilitate an interesting way to count up the overall work done by the algorithm and will greatly facilitate the analysis. So specifically, what is this tree? So at level 0, we have a root. And this corresponds to the outer call of merge sort. Okay, so I'm going to call this level 0. Now this tree is going to be binary in recognition of the fact that each invocation of merge sort makes 2 recursive calls. So the 2 children will correspond to the 2 recursive calls of merge sort. So at the root we operate on the entire input array. So let me draw a big array indicating that. And at level 1 we have one subproblem for the left half and another subproblem for the right half of the input array. And I'll call these first 2 recursive calls level 1. Now, of course, each of these 2 level 1 recursive calls will themselves make 2 recursive calls, each operating on then a quarter of the original input array. So those are the level 2 recursive calls, of which there are 4, and this process will continue until eventually the recursion bottoms out in base cases when there's only an array of size 0 or 1. So now I have a question for you, which I'll give you in the form of a quiz, which is at the bottom of this recursion tree corresponding to the base cases, what is the level number at the bottom? So at what level do the leaves in this tree reside? Okay, so hopefully you correctly guess that the answer is the second one. So namely that the number of levels of the recursion tree is essentially logarithmic in the size of the input array. The reason is basically that the input size is being decreased by a factor 2 with each level of the recursion. If you have an input size of n at the outer level, then each of the first set of recursive calls operates on an array of size n over 2. At level 2, each array has size n over 4, and so on. Where does the recursion bottom out? Well, down at the base cases where there's no more recursion, which is where the input array has size 1 or less. So in other words, the number of levels of recursion is exactly the number of times you need to divide n by 2 until you get down to a number that's at most 1. And recall that's exactly the definition of the logarithm base 2 of n. So since the first level is level 0 and the last level is level log base 2 of n, the total number of levels is actually log base 2 of n plus 1. And when I write down this expression, I'm here assuming that n is a power of 2, which is not a big deal. I mean, the analysis is easily extended to the case where n is not a power of 2. But this way, we don't have to think about fractions. Log base 2 of n then is an integer. Okay, so let's return to the recursion tree. Let me just redraw it really quick. So again, down here at the bottom of the tree, we have the leaves, i.e. the base cases where there's no more recursion, which when n is a power of 2 correspond exactly to single element arrays. So that's the recursion tree corresponding to an invocation of merge sort, and the motivation for writing down, for organizing the work performed by merge sort in this way is it allows us to count up the work level by level, and we'll see that that's a particularly convenient way to account for all of the different lines of code that get executed. Now to see that in more detail, I need to ask you to identify a particular pattern. So first of all, the first question is, at a given level j of this recursion, exactly how many distinct subproblems are there as a function of the level j? That's the first question. The second question is, for each of those distinct subproblems at level j, what is the input size? So what is the size of the array which is passed to a subproblem residing at level j of this recursion tree? So the correct answer is the third one. So first of all, at a given level j, there's precisely 2 to the j distinct subproblems. There's one outermost subproblem at level 0. It has 2 recursive calls. Those are the 2 subproblems at level 1, and so on. In general, since merge sort calls itself twice, the number of subproblems is doubling each level, so that gives us the expression 2 to the j for the number of subproblems at level j. On the other hand, by a similar argument, the input size is halving each time. With each recursive call, you pass it half of the input that you were given. So at each level of the recursion tree, we're seeing half of the input size of the previous level. So after j levels, since we started with an input size of n, after j levels, each subproblem will be operating on an array of length n over 2 to the j. Okay, so now let's put this pattern to use and actually count up all of the lines of code that merge sort executes. And as I said before, the key idea is to count up the work level by level. Now, to be clear, when I talk about the amount of work done at level j, what I'm talking about is the work done by those 2 to the j invocations of merge sort, not counting their respective recursive calls, not counting work which is going to get done in the recursion lower in the tree. Now recall, merge sort is a very simple algorithm. It just has 3 lines of code. First, there's a recursive call, so we're not counting that. Second, there's another recursive call. Again, we're not counting that at level j. And then third, we just invoke the merge subroutine. So really, outside the recursive calls, all that merge sort does is a single invocation of merge. Further, recall we already have a good understanding of the number of lines of code that merge needs. On an input of size m, it's going to use at most 6m lines of code. That's an analysis that we did in the previous video. So let's fix a level j. We know how many subproblems there are, 2 to the j. We know the size of each subproblem, n over 2 to the j, and we know how much work merge needs on such an input. We just multiply by 6, and then we just multiply it out, and we get the amount of work done at a level j. Okay, at all of the level j subproblems. So here it is in more detail. All right, so we start with just the number of different subproblems at level j, and we just noticed that that was at most 2 to the j. We also observed that each level j subproblem is passed an array as input, which has length n over 2 to the j. And we know that the merge subroutine, when given an input, given an array of size n over 2 to the j, will execute at most 6 times that many number of lines of code. So to compute the total amount of work done at level j, we just multiply the number of problems times the work done per subproblem, and then something sort of remarkable happens. We get this cancellation of the 2 to the j's, and we get an upper bound, 6n, which is independent of the level j. So we do at most 6n operations at the root, we do at most 6n operations at level 1, at level 2, and so on. Okay, it's independent of the level. Morally, the reason this is happening is because of a perfect equilibrium between 2 competing forces. First of all, the number of subproblems is doubling with each level of the recursion tree, but secondly, the amount of work that we do per subproblem is halving with each level of the recursion tree. Since those 2 cancel out, we get an upper bound 6n, which is independent of the level j. Now, here's why that's so cool, right? We don't really care about the amount of work just at a given level. We care about the amount of work that merge sort does ever, at any level. But if we have a bound on the amount of work at a level which is independent of the level, then our overall bound is really easy. What do? We just take the number of levels, and we know what that is. It's exactly log base 2 of n plus 1. Remember, the levels are 0 through log base 2 of n inclusive. And then we have an upper bound 6n for each of those log n plus 1 levels. So if we expand out this quantity, we get exactly the upper bound that was claimed earlier, namely that the number of operations merge sort executes is at most 6n times log base 2 of n plus 6n. So that, my friends, is a running time analysis of the merge sort algorithm. That's why its running time is bounded by a constant times n log n, which, especially as n grows large, is far superior to the more simple iterative algorithms like insertion or selection sort. Having completed our first analysis of an algorithm, namely an upper bound on the running time of the merge sort algorithm, what I want to do next is take a step back and be explicit about three assumptions, three biases that we made when we did this analysis of merge sort and interpreted the results. These three assumptions we will adopt as guiding principles for how to reason about algorithms and how to define a so-called fast algorithm for the rest of the course. So the first guiding principle is that we used what's often called worst case analysis. By worst case analysis, I simply mean that our upper bound of 6n log n plus 6n applies to the number of lines of executed for every single input array of length n. We made absolutely no assumptions about the input, where it comes from, what it looks like, beyond what the input length n was. Put differently, if hypothetically we had some adversary whose sole purpose in life was to concoct some malevolent input designed to make our algorithm run as slow as possible, the worst this adversary could do is upper bounded by this same number, 6n log n plus 6n. Now, this sort of worst case guarantee popped out so naturally from our analysis of merge sort, you might well be wondering, what else could you do? Well, two other methods of analysis, which do have their place, although we won't really discuss them in this course, are quote-unquote average case analysis and also the use of a set of pre-specified benchmarks. By average case analysis, I mean you analyze the average running time of an algorithm under some assumption about the relative frequencies of different inputs. So for example, in the sorting problem, one thing you could do, although it's not what we did here, you could assume that every possible input array is equally likely and then analyze the average running time of an algorithm. By benchmarks, I just mean that one agrees up front about some set, say 10 or 20, benchmark inputs which are thought to represent practical or typical inputs for the algorithm. Now, both average case analysis and benchmarks are useful in certain settings, but for them to make sense, you really have to have domain knowledge about your problem. You need to have some understanding of what inputs are more common than others, what inputs better represent typical inputs than others. By contrast, in worst case analysis, by definition, you're making absolutely no assumptions about where the input comes from. So as a result, worst case analysis is particularly appropriate for general purpose subroutines. Subroutines that you design without having any knowledge of how they will be used or what kind of inputs they will be used on. And happily, another bonus of doing worst case analysis, as we will in this course, it's usually mathematically much more tractable than trying to analyze the average performance of an algorithm under some distribution over inputs, or to understand the detailed behavior of an algorithm on a particular set of benchmark inputs. This mathematical tractability was reflected in our merge sort analysis, where we had no a priori goal of analyzing the worst case per se, but it's naturally what popped out of our reasoning about the algorithm's running time. The second and third guiding principles are closely related. The second one is that in this course, when we analyze algorithms, we won't worry unduly about small constant factors or lower order terms. We saw this philosophy at work very early on in our analysis of merge sort. When we discussed the number of lines of code that the merge subroutine requires, we first upper bounded it by 4m plus 2 for an array of length m, but then we said, let's just think about it as 6m instead. Let's have a simpler, sloppy upper bound and work with that. So that was already an example of not worrying about small changes in the constant factors. Now, the question you should be wondering about is, why do we do this, and can we really get away with it? So let me tell you about the justifications for this guiding principle. So the first motivation is clear, and we used it already in our merge sort analysis, which is it's simply way easier mathematically if we don't have to precisely pin down what the leading constant factors and lower order terms are. The second justification is a little less obvious, but is extremely important. So I claim that given the level at which we're describing and analyzing algorithms in this course, it would be totally inappropriate to obsess unduly about exactly what the constant factors are. Recall our discussion of the merge subroutine. So we wrote that subroutine down in pseudocode, and we gave an analysis of 4m plus 2 on the number of lines of code executed, given an input of length m. We also noted that it was somewhat ambiguous exactly how many lines of code we should count it as, depending on how you count loop increments, and so on. So even there, small constant factors could creep in, given the underspecification of the pseudocode. Depending on how that pseudocode gets translated into an actual programming language, like C or Java, you'll see the number of lines of code deviate even further. Not by a lot, but again by small constant factors. When such a program is then compiled down into machine code, you'll see even greater variance depending on the exact processor, the compiler optimizations, the programming implementation, and so on. So to summarize, because we're going to describe algorithms at a level that transcends any particular programming language, it would be inappropriate to specify precise constants. The precise constants will ultimately be determined by more machine-dependent aspects, like who the programmer is, what the compiler is, what the processor is, and so on. And now the third justification is, frankly, we're just going to be able to get away with it. That is, one might be concerned that ignoring things like small constant factors leads us astray, that we wind up deriving results which suggest that an algorithm is fast when it's really slow in practice, or vice versa. But for the problems that we discuss in this course, we'll get extremely accurate predictive power, even though we won't be keeping track of lower order terms and constant factors. When the mathematical analysis we do suggests that an algorithm is fast, indeed it will be. When it suggests that it's not fast, indeed that will be the case. So we lose a little bit of granularity of information, but we don't lose in what we really care about, which is accurate guidance about what algorithms are going to be faster than others. So the first two justifications, I think, are pretty self-evident. This third justification is more of an assertion, but it's one we'll be backing up over and over again as we proceed through this course. Now, don't get me wrong. I'm not saying constant factors aren't important in practice. Obviously, for crucial programs, the constant factors are hugely important. If you're running the sort of crucial loop for, that your startup's survival depends on, by all means, optimize the constant like crazy. The point is just that understanding tiny constant factors in the analysis is an inappropriate level of granularity for the kind of algorithm analysis we're going to be doing in this course. Okay, let's move on to the third and final guiding principle. So the third principle is that we're going to use what's called asymptotic analysis, by which I mean we will focus on the case of large input sizes, the performance of an algorithm as the size n of the input grows large, that is, tends to infinity. Now, this focus on large input sizes was already evident when we interpreted our bound on merge sort. So how did we describe the bound on merge sort? We said, oh, well, it needs a number of operations proportional, a constant factor times, n log n. And we very cavalierly declared that this was better than any algorithm which has quadratic dependence of its running time on the number of operations. So for example, we argued that merge sort is a faster algorithm than something like insertion sort without actually discussing the constant factors at all. So mathematically, we were saying the running time of merge sort, which we know we can represent as the function 6n log base 2 of n plus 6n, is better than any function which has a quadratic dependence on n, even one with a small constant, like let's say 1/2 n squared, which might be roughly the running time of insertion sort. And this is a mathematical statement that is true if and only if n is sufficiently large. Once n grows large, it's certainly true that the expression on the left is smaller than the expression on the right, but for small n, the expression on the right is actually going to be smaller because of the smaller leading term. So in saying that merge sort is superior to insertion sort, the bias is that we're focusing on problems with large n. So the question you should have is that reasonable? Is that a justified assumption to focus on large input sizes? And the answer is certainly yes. So the reason we focus on large input sizes is because, frankly, those are the only problems which are at all interesting. If all you need to do is sort 100 numbers, use whatever method you want, and it's going to happen instantaneously on modern computers. You don't need to know, say, the divide and conquer paradigm if all you need to do is sort 100 numbers. So one thing you might be wondering is if, with computers getting faster all the time, according to Moore's law, if really it doesn't even matter to think about algorithmic analysis, if eventually all problem sizes will just be trivially solvable on super fast computers. But in fact, the opposite is true. Moore's law, with computers getting faster, actually says that our computational ambitions will naturally grow. We naturally focus on ever larger problem sizes, and the gulf between an n squared algorithm and an n log n algorithm will become ever wider. A different way to think about it is in terms of how much bigger a problem size you can solve as computers get faster. If you're using an algorithm with a running time which is proportional to the input size, then if computers get faster by a factor of 4, then you can solve problems which are a factor of 4 larger. Whereas if you're using an algorithm whose running time is proportional to the square of the input size, then if computers get faster by a factor of 4, you can only solve double the problem size. And we'll see even starker examples of this gulf between different algorithmic approaches as time goes on. So to drive this point home, let me show you a couple of graphs. So what we're looking at here is we're looking at a graph of two functions. So the solid function is the upper bound that we proved on merge sort. So this is going to be 6n log base 2 of n plus 6n. And the dotted line is a estimate, a rather generous estimate about the running time of insertion sort, namely 1/2 times n squared. And we see here in the graph exactly the behavior we discussed earlier, which is that for small n, down here, in fact, because 1/2 n squared has a smaller leading constant, it's actually a smaller function. And this is true up to this crossing point of maybe 90 or so. But then beyond n equal 90, the quadratic growth in the n squared term overwhelms the fact that it had a smaller constant, and it starts being bigger than this other function, 6n log n plus 6n. So in the regime below 90, it's predicting that insertion sort will be better, and in the regime above 90, it's predicting that merge sort will be faster. Now here's what's interesting. Let's scale the x-axis. Let's look well beyond this crossing point of 90. Let's just increase it in order of magnitude up to arrays of size 1500. And I want to emphasize these are still very small problem sizes. If all you need to do is sort arrays of size 1500, you really don't need to know divide and conquer or anything else I'll talk about. That's a pretty trivial problem on modern computers. So what we're seeing is that even for very modest problem sizes, here array of size say 1500, the quadratic dependence in the insertion sort bound is more than dwarfing the fact that it had a lower constant factor. So in this large regime, the gulf between the two algorithms is growing, and of course if I increased it another 10x or 100x or 1000x to get to genuinely interesting problem sizes, the gap between these two algorithms would be even bigger. It would be huge. That said, I'm not saying you should be completely ignorant of constant factors when you implement algorithms. It's still good to have a general sense of what these constant factors are. So for example, in highly tuned versions of merge sort, which you'll find in many programming libraries, in fact, because of the difference in constant factors, the algorithm will actually switch from merge sort over to insertion sort once the problem size drops below some particular threshold, say 7 elements or something like that. So for small problem sizes, you use the algorithm with smaller constant factors, namely insertion sort. For larger problem sizes, you use the algorithm with better rate of growth, namely merge sort. So to review, our first guiding principle is that we're going to pursue worst case analysis. We're going to look to bounds on the performance, on the running time of an algorithm, which make no domain assumptions, which make no assumptions about which input of a given length the algorithm is provided. The second guiding principle is we're not going to focus on constant factors or lower order terms. That would be inappropriate given the level of granularity at which we're describing algorithms. And third is we're going to focus on the rate of growth of algorithms for large problem sizes. Putting these three principles together, we get a mathematical definition of a fast algorithm. Namely, we're going to pursue algorithms whose worst case running time grows slowly as a function of the input size. So let me tell you how you should interpret what I just wrote down in this box. So on the left-hand side is clearly what we want. Okay, we want algorithms which run quickly if we implement them. And on the right-hand side is a proposed mathematical surrogate of a fast algorithm. Right? The left-hand side is not a mathematical definition. The right-hand side is, as will become clear in the next set of lectures. So we're identifying fast algorithms, which those that have good asymptotic runtime, running time which grows slowly with the input size. Now, what would we want from a mathematical definition? We'd want a sweet spot. Okay, on the one hand, we want something we can actually reason about. This is why we zoom out and squint and ignore things like constant factors and lower order terms. We can't keep track of everything, otherwise we'd never be able to analyze stuff. On the other hand, we don't want to throw out the baby with the bathwater. We want to retain predictive power. And this definition turns out for the problems we're going to talk about in this course to be the sweet spot for reasoning about algorithms. Okay, worst case analysis using the asymptotic running time. We'll be able to prove lots of theorems. We'll be able to establish a lot of performance guarantees for fundamental algorithms, but at the same time, we'll have good predictive power. What the theory advocates will in fact be algorithms that are well known to be fast in practice. So the final explanation I owe you is what do I mean by the running time grows slowly with respect to the input size? Well, the answer depends a little bit on the context, but for almost all of the problems we're going to discuss, the holy grail will be to have what's called a linear time algorithm, an algorithm whose number of instructions grows proportional to the input size. So we won't always be able to achieve linear time, but that's in some sense the best case scenario. Notice linear time is even better than what we achieved with our merge sort algorithm for sorting. Merge sort runs a little bit superlinear. It's n times log n, where n is the input size. If possible, we'd love to be linear time. It's not always going to be possible, but that is what we will aspire toward for most of the problems we'll discuss in this course. Looking ahead, the next series of videos is going to have two goals. First of all, on the analysis side, I'll describe formally what I mean by asymptotic running time. I'll introduce big O notation and its variants, explain its mathematical definitions, and give a number of examples. On the design side, we'll get more experience applying the divide and conquer paradigm to further problems. See you then.